Okay. Technology finally agreed with me. My. I have a fairly new car, it's only got 20,000 miles on it. Every now and then the battery stops. I had a little battery. That has 1,000 amps in it for a second and a half. It started right up, the new battery, and put there, not a new battery, but recharge. We're getting off. Anyway, yeah,
What kind of car is it?
the cameras.
Pretty for my camera. How's it?
It's, my license plate's Camfrog. So I was surprised that wasn't, taken already. But, I tried, I used to be a ham operator, radio operator, and I knew Morse code, so I was gonna put that's a Morse code on my license plate. And when hams go by, and they know you're another hand, they'll go, which is high in Morse code. Now, the put Tom, and it's really easy, da, 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 da. Really easy, but you can't just put numbers for your license, but you have to have output numeric. That's all right, what the heck, Chemprop went through. Weird. Anyway, yes, I had the same comment about the Camry, why? I mean, I've had old Camrys in the past for years and years. Rarely my car. I take care of my car a lot, change over a couple of miles, you know. Anyway. Okay, we're gonna continue on to talk about the history of the atom today. And get us into the different models we're using. And you're gonna kind of learn some challenges that scientists, physicists have had in the years. All right, and this is a PowerPoint that is available on Canvas. It's called History of Science. And no, I don't know where it is on Canvas. I know it's difficult. All right, so let's go back to the Greeks, thousands of years ago. There were two main philosophers, I guess they were philosophers. I don't know if they were called scientists in those days. Aristotle and Democritus. And they had very different views about matter. The popular one was Aristotle, and he thought all matter was composed of four elements: earth, air, fire, and water. I always say earth, wind, and fire, but it's not the group. Earth, air, fire, water. And that lasted until the 1700s. So it lasted over pushing almost 3,000 years. The other guy at the same time period, his name was Democritus, and he believed that of this concept of the atom. In fact, in Greek, it's called atomos. And atomos in Greek stands for no cut. And what they mean is if you take an apple, for example, and you started cutting it, cut it in half, it's still an apple. Cut it in half again, still an apple. Okay, we're going to keep cutting it until it doesn't become an apple anymore. And that's what Democritus was saying, that everything is down to that small level. And again, these were around for a long, long time. And during the Middle Ages, the rise of the alchemists, and their main mission was to create gold from cheap metals like lead. And they didn't do a very good job. We can do that now. It's very expensive to do, but we can do it. It's done naturally also, and the atmosphere is done naturally. Their main goal was to please the king from whom they worked. They paid their, living and stuff. But the group of alchemists, though, was looking as a group. We're looking for the elixir of life. and this thing called ether. And everyone had a different idea of what that was. That was one of the problems. But they were very popular and they were around for hundreds of years. There are two main issues with alchemy. In today's science, when we find something, like a new element or something like that, another scientific group has to replicate that process we use. They didn't do that in those days. They just said, I got something new. There was no one, not another group that was in close proximity that could verify it or had the wherewithal or interest in verifying it. And also, if you think about the Dark Ages, you look at London, look at Paris, those were villages. They weren't very big and they were really far apart. And how do you go from one village to the next village in those days? Well, you either walk or you were on a donkey. That's about it. So communication was extremely poor and extremely slow. So that was another reason why the first idea there, the scientific method, didn't work so well. It's because they lacked communication. And then the other problem was there was no standardization on anything. They didn't have any common knowledge like we do now. Like, for example, on naming things. For example, water. What is water? That's the scientific formula. Or dihydrogen monoxide is the scientific name, but it's called water in English, right? Aqua, Spanish. Every language has got another name for water, but it's not water. But in every language, dihydrogen monoxide is the scientific name for water in every language, whether it be Spanish, Russian, whatever. So that was another problem. So it's hard to come up with a scientific method if the language is not there. So those two were major roadblocks for the success of alchemy. Now, another interesting thing is that a lot of people think of Europe when they think of scientists. Well, sorry, Europe, but in the middle, around 1000 AD, 9th century, the Middle East was the hotbed of science. And even before that was Asia. It wasn't until like the 1700s, not counting alchemy, 1700s that Europe can join the group of scientists. The first guy, his name was Dalton. Now, for this class, I want you to have a one-liner for each one of these people. Like Democritus, atom. Dalton, first theory, first atomic theory. And he came back with Democritus's atom. It's the first time since Greek times they reintroduced the concept of the atom. These are the 5 tenets of his claim to fame. Okay, matter is composed of indivisible particle atoms. Democritus. All atoms of a particular element are identical. If you've got a piece of gold, all the atoms are gold if it's pure. I mean, it's like duh. Different elements have different atoms. It's kind of opposite of number 2. Atoms combine in certain whole number ratio. This is a big deal. For example, you mentioned the formula for water H2O. It's not H 2.10. It's exactly 2 and exactly 1 integers. And the last one, we're going to talk a lot about what is a chemical reaction. He stated chemical reactions atoms are merely rearranged to form new compounds, which is mostly true, except for one huge exception, nuclear reaction. They don't do that. They are a different way of doing that. The basic number 5 says you take what you start with, you pull it apart, rearrange it. That's the chemistry we're going to talk about in here. It's just that. But nuclear energy doesn't work like this. Okay, remember yesterday we talked about elements with different numbers of protons are different elements. If you change the protons, you change the element. And that's where that differs from number 5 there. Okay, and this is stating what I just mentioned about 1 through 4. Okay, the next guy came along, his name is Thomson. He's credited for 2 things. The electron and the first model of matter, which is called the plum pudding model. And what he means by that is everything is just stuffed into that atom and no organization at all, just crammed in there. And this is what he looks like. In fact, he called the electrons corpuscles. Now, he also had a back-end way of discovering protons, because electrons are negatively charged, and the atom he was looking at was neutrally charged, no charge at all. So something had to be in there to offset that negative charge. That's all he said. There's no proof, nothing, no experiment to prove it or anything like that. Now, Thomson did not know how negative the electrons were. Charges are measured in coulombs, and he didn't know how much that electron was charged. Millikan determined that actual charge. Very famous lab called the oil drop experiment. So Millikan, electron charge. Now, this was the most controversial statement. Came from a guy named Rutherford. Rutherford decided to test Thomson's model. Now, remember we talked about scientists have to replicate things you say as a scientist. You do that by publishing, and then other people repeat what you've done to make sure what you've done is valid. That's what Rutherford was doing with Thomson's plum pudding model. So he devised an experiment where he shot a gold foil with a bullet, and that bullet was an alpha particle. Now, alpha particles, according to at the subatomic scale, are really large. Right? 2 neutrons and 2 protons, big. Electron is 1/30,000th that size. So that's the relative size of these 2 particles. But he shot the gold foil with this bullet. And he had the source of the bullet over here and blah, blah, blah. Let me see. So this was a alpha source. And when you shot that thing, now if you have a pool ball, billiard ball, and you shoot it with the cue ball, does the ball you're shooting break apart? No, it does what? It bounces, transfers energy, but it bounces. Sometimes it bounces straight back, sometimes to the right, sometimes to the left. So that's what he was expecting this to happen. When he shot the gold foil, he was expecting it to just bounce off that. And he had detectors around the gold foil to detect that. However, his experiment did something very, very different. Everything went through the gold foil, except about 0.1% bounced. Everything went through, which was an enigma. How can this happen? So Rutherford said, well, there's something in there for sure, because the bullets are bouncing off. But they weren't bouncing off everywhere, just in a very tiny, tiny place. Tiny, tiny place is called the nucleus. So almost all the mass of an atom is in that tiny little spot. There was another challenge in that tiny spot, protons. What charge do protons have? Positive. Positive proton next to a positive proton repels each other. So what's keeping them together in that tiny little spot? That's the energy that is released when we talk about nuclear energy. It's called strong force. Very, very strong to keep those. Now, let me give you a relative size here. If we take the atom the size of a professional football field, and on the 50-yard line in the middle, we put a marble there. That's the relative size of the nucleus compared to the whole atom. It's huge difference, huge. So Rutherford was a big guy in science. He didn't get the Nobel Prize for this, though. He got it for doing some nuclear energy stuff, interestingly. Now, think about this. Okay, let's go back 100 years. And I told you, you're walking on nothing. That's nothing. Is that pretty hard to believe? I think it is, yeah. And here he is saying, well, I've got proof. That's the only way to rationalize the results I got from this experiment is that there's nothing there, going right through, unadulterated, right through. So it was really a challenging thing to come up with. Okay. Chadwick came up with concept of the neutron. And he claimed the mass of the proton and the neutron were the same. They're not the same. They're close, but they're not the same. They differ by the mass of an electron, because neutrons are made up of a neutron and an electron. But anyway, and he said they're also non-charged. So mass of the proton, non-charged. Ashton came up with a concept of the isotope. When we mentioned isotopes yesterday, remember carbon-14, carbon-12, only difference between the two are two neutrons. So isotopes differ in the number of neutrons. Oops. So the number of protons are equal. The number of neutrons are not equal for an isotope. But 100 years ago-ish, Bohr came up with this concept. He said that's hogwash, that electrons are not organized inside the atom. So he developed this really fancy math. I mean, really, to get a degree in chemistry, you got to take a whole semester of quantum mechanics. And it uses all that fancy calculus and differential equations and all this wild math. And this is what Bohr came up with. He based it on the planetary model of our solar system. Remember in Men in Black? What was on Orion's collar? Galaxy, that's right. Orion was the name of the cat. And the galaxy was on a little charm on the collar. So there was a galaxy which revolves around the solar system like model. Then there's solar systems within that galaxy also have masses revolving around them. And so he said, it seems natural that the atoms are set up the same way. And he had math to prove it too. So he defined something called an orbital. Orbital says we've got orbitals starting closest to the nucleus and going out. Because the orbitals, as you get further away from the nucleus, are bigger, then it can hold more electrons. The most inner orbital in Bohr's model can only hold 2 electrons. It's also the most stable orbital because electrons are charged negatively, nucleus is charged positively, and they attract one another. So that's the reason why it's so stable. But only a certain number can fit in these orbitals, no more than that. But less in, but not more than this number. The numbers are 2, 8, 8, 18, etc. That's for organizational purposes. Now, there's another important thing about Bohr's idea. Now, this has to do with stability. If something is stable, like this pen here, and we want to move it to something that is less stable, it requires energy. Kinetic energy is going to move it from there to here. Now, it's unstable here compared to here. So what does it want to do? It wants to return to that stable state. Electrons do the same thing. These fluorescent lights are showing you Bohr's model as we speak. The way fluorescent light works is we shoot it with a bunch of energy. So inside the fixture, there's a black box, and it produces a whole bunch of voltage, like 15,000 volts, really a lot. Okay, and what that does, we zap the electrons and there's molecules in there. Usually it's some kind of a neon gas or something like that. And what happens is we zap the electrons from a stable orbit to an unstable orbit. And those electrons now want to go back to the stable state. So what they do is they go with it. When they go there, they release the energy it took to get them there. And if the energy released is in the visible spectrum, we see it. But usually it's all over the place. Just a small portion is invisible. And depending on the gas you're exciting, a whole bunch of parameters, but basically that's it. LEDs, another example. Laser light, another example. All those have to do with electrons moving orbitals. Every single one of those. So it takes energy to get to the unstable state, and energy is given off as it comes back down to the more stable state. That's what part of Bohr's model. And this is really a big deal. Now, this has not changed, this concept. The planetary model has changed. Okay, there's the excited state and ground state. Ground state is the most stable. Excited is after the electron has been zapped. Now we are here. We're at the quantum model. The quantum model is basically a statistical model. And the class I hated most when I was undergraduate was statistics. And here I am taking a class in quantum mechanics that requires statistics. Anyway, let me give you an example of how this works. There are orbitals in the quantum model as well. They're just not like the models in the Bohr orbitals. They're very different. So, if we're at Rayleigh's, on the side of the building, there's a door. And when you come into Rayleigh's at this door, there's a whole bunch of cigarette butts on the ground. We don't know where they came from. We don't know if an employee was out there smoking. We don't know if a customer. We don't know if a homeless person. We don't know where they came from. But we know where to find them. Side door at Rayleigh's. Now, what are the chances of a cigarette butt being found in here? High or low?
What?
Really low, right? Not zero. Not zero, but really, really low. Okay, that's the quantum model. Is we know where to find electrons around the nucleus. We don't know how they got there, though. So statistical probability comes into play where we can have a certain probability of finding an electron in a certain location. And the orbitals, one of them is circular. All the others are weird shaped. The first level is called S orbitals, and that's kind of like planetary model. 3-dimension though, not 2-dimension. That was another problem with Bohr's model. It was a 2-dimensional model, not a 3-dimensional model. The next one follows the XYZ axes, globes. And then from there, the next level out, it fills in between the nodes. And then it keeps getting more and more complex. So those are named. The first simplest one is S. I'm going to talk in depth about this later, but basically the simplest orbital is called the S. The next simplest is called P, then D, then F. So there are 4 different orbitals. F is the most complex, carries the most electrons. Like uranium has 92 electrons, for example. And then the other thing is, what they do is they assign 4 designations or 4 names so they can locate any electron in the atom by using these 4 numbers. And don't write this down because we're going to have a whole unit, part of a unit on this. But there's shell, subshell, orbitals in the subshell, and spin of the electrons. So that's where we are now. And the model is not perfect, but it answers a lot of questions about things that weren't answerable before. Okay, so it's 1:16, and our lab's needs to start here pretty soon. So I'm going to end it here. And